All right, good morning, everyone. Most of you are here. If you're already struggling on the second day to make 9 o'clock, that's a problem. But well done for all of you who are here. Okay, so let me just briefly review what we did yesterday, and then I'll tell you what we're going to do today. So yesterday we looked at the dark matter landscape. I drew this large range of masses covering many, many orders of magnitude. We talked a little bit about how there's different bounds, very generic bounds. So for bosons, very roughly has to be above 10⁻21, 10⁻22 electron volts or so. For fermions, because of the Pauli extrusion principle, has to be a bit heavier, at least a keV, maybe hundreds of eV. Then we had on the other end of the mass range, we said that's interesting because of LIGO events potentially. Okay. So we didn't go into any details, but I just sort of mentioned it. And if you're interested, I gave some references, which you can look up. And then we talked about that if we make additional assumptions about the dark matter, then we have additional constraints of what it might be. So if we assume that it was in thermal equilibrium, for example, then the mass range is restricted. And here, of course, I've blown it up on the scale, but it's, compared to the whole possible scale, it's very small. So we talked about that there's a warm dark matter mass limit at around a keV. So if you're below that and you're in thermal equilibrium with the standard model in the early universe, if you're very hot, then you will not form dwarf galaxies below, if the mass is below a keV. And these are just rough bounds, okay? And on the other hand, we've got a 100 TeV bound, which comes from unitarity, where you just can't make the cross-section large enough to annihilate the dark matter particles away, okay? And the basic idea about the thermal dark matter, which we briefly mentioned for WIMPs, that I drew this diagram where we looked at the abundance of dark matter as a function of time. And if it remains in thermal equilibrium, there's an exponential suppression after a while, where basically you don't get any dark matter left over. But if it decouples, which it should do because the universe expands and dilutes, so the dark matter particles have a harder time finding each other, and then they can't annihilate your standard model particles anymore, and they get frozen in, the abundance gets frozen in. So at some point, this will level off, and the level at which the place at which this levels off is given by the annihilation strength. So how strong is this annihilation cross-section of dark matter to standard model particles? And the cross-section that you need to get the right abundance is, you can calculate it, and it depends a little bit on the mass, but not much, and it's about a picobarn. And a picobarn is what you would get from the weak interactions. Okay, so that's why a WIMP, a weakly interacting massive particle, is a good dark matter candidate. And the other so this points to the weak scale, or the 100 GeV scale, for the existence of dark matter. And the other reasons why we think there should be new particles, new physics at the weak scale, namely the hierarchy problem, which Nathaniel is going to go into more detail in his lectures. But there's sort of two independent things that point to the weak scale, which makes this very interesting. And then we talked briefly about lots of searches going on for dark matter particles with this, for WIMPs, basically. Okay. So one thing is that we said that this dark matter particle freezes out when it's non-relativistic, and that's true, but just to be clear, the velocity of the dark matter particles when they freeze out is still quite high. So typically it's about 0.3, and the temperature at which the dark matter decouples is typically about a 20th of the dark matter mass. So I haven't derived that, but it's that's something you can show. So they're still pretty fast moving, but they're non-relativistic, but they still move pretty quickly. Okay. But a picobarn is roughly what you would want. Okay. So then, getting back to this diagram, so there's other bounds that in principle you have to worry about, which if this were purely lectures on dark matter, I would go into more detail. But if you really have dark matter that's in thermal contact with the standard model particles, you have to worry about other things. So here we worried about the structure formation bound. So here's a unitarity bound. But actually below an MeV, you have to worry about bound from Big Bang nuclear synthesis, so BBN. So if you have dark matter that's in thermal equilibrium with the standard model particles at around an MeV, around the time that BBN starts, so that's when neutrinos decouple and you start forming the nuclei, then you if the dark matter is in thermal equilibrium, it actually affects the expansion rate of the universe at that time, and it would change the predictions of BBN, which are in pretty good agreement with what, with just pure standard model. So that can give you trouble. So I made this sort of a long dash line that if you really have thermal dark matter, you have to worry or work hard a little bit to get around BBN bounds below an MeV. But at least above an MeV, you're pretty safe. So I'm not going to go into more details. If someone wants, we can discuss it afterwards. But this is roughly the region, and below an MeV, you have to work too hard. Below a keV, you have to work much, much harder even, okay, to get around this from a model building point of view. So let me talk about now this line here, the WIMPs. So I drew this from 100 TeV down to a few GeV or GeV or so. And let's just talk about the idea of dark matter freezing out with a heavy mediator, so with a WZ boson. So in particular, I want to explain the lower bound here, around a GeV. Okay, where is that coming from? And here what we have is we've got dark matter that's pretty light, GeV, interacting with heavy-ish particles like the WZ boson. And let's quickly look at where this comes from. So there's a bound called the Lee-Weinberg bound. Before I go on, so any questions on this? This is just a summary quickly. Okay, so let's talk about the Lee-Weinberg bound for WIMPs. And what we're going to do is we're going to take a prototypical WIMP, like a heavy Dirac neutrino, which couples to the Z boson. Okay, there's nothing WIMPier than that. So it's charged under some neutrino, some heavy neutrino, which is charged under SU2 cross U1. And we're going to consider small masses. I'm going to note the dark matter with chi often. So we're going to consider dark matter masses less than the WZ boson mass, which are our force carriers, our mediators. And we're going to consider the following diagram. So this can annihilate two standard model particles as follows. Where this is a Z boson. So that's basically the blob that I drew over there is now the Z boson. Okay. And we can calculate this cross section, so we can do this very carefully, or we can estimate it from dimensional analysis. So if the mass of this thing is light, what does the cross section roughly have to scale as? Yeah, so we're going to write down sigma. So you said 1 over the mass of the Z. Okay. So what are the dimensions of the cross section? Okay, 1 over, oh, I hear square, but I don't hear the first part. 1 of the mass squared, right? Okay, so you're saying it should be something like this? Okay, who agrees? You agree? Okay, who disagrees? Yeah? You had your hand up. Do you disagree? You agree?
Yeah. Well, if the amplitude is going to have 1 on the end square, it should be probably
right. So it should be to the 4th?
Yeah.
Okay. So we have another suggestion. Okay, so everyone who'd agreed before should now disagree with this. So
probably throw in a G Fermi somewhere.
Okay, you can do G Fermi, yeah. Okay, somewhere, yes. That's right. Yeah, but we don't care about angular dependence. Okay, we just want mass dimensions, right? Okay, so you're right. There's a propagator, which is 1 of mz squared, which then gets squared. That's order mz to the 4th. These are non-relativistic when they freeze out. Okay, so we know that. So what other mass scale do I have in the problem that could be interesting? That in the end, what I want is a 1 over m mass squared, something 1 over mass squared. M chi. Okay, so this could go as m chi squared. Okay. And then you have to worry in principle about factors of pi, right? And then of course coupling constants as well. So we know how the Z couples to the standard model fermions. We said this is a Dirac neutrino, so we know how the Z couples to this chi in particular as well. We throw in the right G's, G primes, etc. And then someone mentioned Fermi constant, I forget where it was, maybe you. Okay, so basically, so this is all right, so times factors of times couplings to some fourth power and then some pi's. So the way you can write this at the end is, turns out you can write this as 1 over, as sigma as G Fermi squared m chi squared over pi. And G Fermi basically is 1 over the mass of the Z to the, or 1 of the mass of the W to the fourth with appropriate couplings. So basically that's what you can calculate, what this should be. Okay, but just from dimension analysis, you know this has to be the right answer. So G Fermi is 10 to minus 5, approximately 1 over GV squared. Okay, so this has 1 over GV to the fourth in the denominator, 1 over GV to the fourth, and then times the GV squared. So it has the right mass dimensions. And what we want, again, is that this should be order picobarnish. Okay, picobarn. So what we can do is we can write this as 1 picobarn. And that happens for, by putting all the numbers right, and this happens for about 5 GV. Okay, so the cross-section is correct. It's about a picobarn for a mass of 5 GV. And what you notice is that for lower masses, the cross-section is smaller, which means that the abundance, the final dark matter abundance, which goes as 1 over sigma. So it's really sigma V, but it doesn't matter. In this case, I don't care. So which really goes as 1 over sigma V, which is going to be, that's going to be too large for m chi below 5 GV. Okay, and this is a problem with heavy mediators, that the cross-section generically will scale as mass squared of the dark matter to the heavy mediator mass to the fourth. And as I lower the dark matter mass, the cross-section is going to get smaller and smaller, which means that I'm going to have more and more dark matter abundance left over. And at some point, it's going to overclose the universe or just be too much. Okay, it just won't fit in compared to what we have. There's nothing wrong with having a large cross-section and then having less dark matter. It just means that this candidate is not going to be all the dark matter. There's going to be other things as well. But you can't have too much of it. So below 5 GV, that's roughly what happens. And that's why roughly around GV, 5 GV or so, that's where the WIMPs will end. Okay. And if you want to have thermal dark matter for lower masses, you can't have heavy mediators. And the dark matter, so what mediators do we have available? We've got the W and Z, which are heavy. We've got the photon, but then the dark matter would be electrically charged. We have the gluons, but then the dark matter would be strongly interacting. There's also very strong constraints on that. So if we want to have light dark matter, we need new mediators, new forces. We need a dark sector. Okay. So let's do that and to show the dependence, how the cross-section scales for light mediators. Okay. So I can evade Lee Weinberg bound with new light mediators. And for example, what I can have is I'll set up a very similar situation, but instead of the Z boson, I'm going to imagine some new vector boson, which I'll just call Z prime, which couples to standard model particles. And in this case, what I have is that this is a light particle. And then how does the cross-section change? Well, sorry. So for now, let me still have so all I want is that the dark matter is, so I want the dark matter to be light, but I'm allowing now the Z prime to have a mass that's not necessarily at 9 GeV, fixed by essentially G Fermi, but I'm allowing it to be lighter. In that case, it's very simple, right? You just have so now I'm going to write it, just the couplings. So G chi is this coupling here, there's a GF coupling on this vertex there, and then I'm going to have an m chi-squared and an mz prime to the fourth. And just putting in some numbers again, I'll get 1 picobarn. I'm going to put in some reasonable values for G chi, G Fermi, not G Fermi, sorry, GF. Put this to -3. Now I've got 100 MeV as my example, squared, and I'm allowing now the Z prime mass to be a GeV. Okay. So very trivially, in some way, right, all we're allowing is that this MZ now is smaller. That makes the cross-section larger, which allows the dark matter also to be lower mass so that you can evade, that you can get a large enough cross-section to not overclose the universe or not be in conflict with observations. Okay. So conclusion is that low mass dark matter is allowed, so with masses below what you would call the WIMP, below what I'm calling at least the WIMP region here, is allowed so it's allowed to be produced from thermal freeze-out if the mediators are light. But again, this requires new mediators. Which by definition, so the dark matter has to interact with some new mediator, which also interacts with the standard model, but this is what I'm calling a dark sector. And there's also an interesting sort of, so let me just first say, so this was first pointed out by Berman Fayet around 2000, 2002 or something, I forget the exact time, but around that time. And sort of an interesting point is that, if you look at these masses here, so here, of course, I can pick up whatever I want, but here I picked a GeV or so. But these couplings are not too small, right? So if you ask what kind of laboratory probes I can have, what kind of dark matter can I probe in a laboratory? If you ask what kind of dark matter can I probe in a laboratory, then having dark matter that's in thermal contact with a standard model is sort of a good guiding principle for many models that are actually probable in the laboratory. Why? Just because the couplings can't be too small. And if you have interactions between dark matter and the standard model particles that are not that small, you can hope to produce the dark matter in a laboratory and measure it in some way. Okay. And we'll talk about how to do that in the next lecture and next 2 lectures or so. Well, in the remaining lectures really. Okay, so thermal dark matter is sort of an interesting thing if you want to look for dark matter candidates that you can probe in a laboratory. It's not the only thing you can probe in a laboratory, but it's something you can probe. And it also shows that this typical WIMP range that we've been focusing on for 2 or 3 decades is not the only story. We really should broaden our views of what we're looking at. And that's happened over the last 10 years, okay, where people have come up with lots of new ideas for experiments to try and probe below the scale, because there's particles that could be sitting there which we just could have missed so far in the existing data. And in many cases, we need new ideas or new experimental techniques or new detector development in order to probe that. And we'll see that, for example, WIMPs, direct detection experiments have been very good at probing WIMPs down to the GeV scale. It's very hard to go lower in mass, but there's new ideas now how to do that. And I'll talk about that a little bit in my last lecture. Okay. So, but this just shows in a maybe trivial way or not, I don't know, but it shows that we really want to expand our searches well below the GeV scale, even just to talk about the simple paradigm of thermal dark matter. And there's other things that the thermal dark matter is not the only thing that's of interest, but it's one of the things. Okay. Good. So then what I'll do now is we'll talk about, well, let me just make some more comments about WIMPs and expanding our searches beyond WIMPs. So here you see an example of why it's good to go beyond WIMPs, just because there's nothing wrong with having even thermal dark matter below the GV scale, below the WIMP window. But there's some other reasons why going beyond WIMPs is interesting, right? So one trivial one is that we haven't seen them. We've been looking for them a long time. We haven't seen them. The thing that made WIMPs interesting is the potential connection to solving the hierarchy problem with new particles at the weak scale. But the LHC hasn't seen any new particles. Okay, so maybe that's just not a good guiding principle either. So we haven't seen any new particles at the LHC that could solve the hierarchy problem. So maybe dark matter is not, maybe the WIMP miracle, as it's often called, is not there either, is not relevant either. And then one thing I haven't talked about, but so there are many different kind of production mechanisms. As I said, even just the thermal dark matter idea, that works well below the GV scale as well. But there's other kinds of interesting dark matter candidates like asymmetric dark matter. People talk about elders, SIMPs. So if you're familiar with the dark matter literature, there's lots of model building going on where theorists are coming up with ideas for dark matter candidates that sit in this mass range going down to MeV, even keV. Okay. And then for fun, just very briefly, I want to mention another reason to go beyond WIMPs, which is problems on small scales with structure formation. So who's heard about, so this is something called, sometimes this is called the small scale crisis of cold dark matter. Who's heard about this? Just a few? Okay, so let me just briefly say some words about this. So many reasons to expand dark matter searches beyond WIMPs. Let me just summarize what I said. So no sign of WIMPs. This always comes with a yet, right? So far. No new physics at LHC yet. There's many known production mechanisms. Not just thermal freezer, but others, which I haven't discussed about, but all those motivate additional searches. And then finally, the small scale crisis of cold dark matter, cold collisionless dark matter. And so the idea that dark matter is a WIMP, for example, that it's cold, right, the way I defined it yesterday, that it basically is that it decouples when it's non-relativistic, and that it doesn't interact much with itself, that works extremely well. So that idea that dark matter has this property works extremely well in terms of structure formation. You can calculate how the dark matter structure forms if you have such a dark matter candidate, and you reproduce the structure that you see in the universe. And you can do the calculation with n-body simulations, and then you compare with data. And it works extremely well, except for small scales, where things don't quite agree yet. And by small scales, I mean scales of order, kiloparsec or so. Okay, and and some of the issues that go under the following names. So there's the core cusp problem, So this is a problem where if you look at the dark matter density distribution on a galaxy or a dwarf galaxy or so in some galaxies I should say, where's my little eraser? So if you take n-body simulations and you just evolve the dark matter structure in the universe, you let structure form, and then you look at what the dark matter density profile is of galaxies and of different sizes, what you find is that as a function of radius, the dark matter density will go something like this. And the inner part grows very roughly as 1 over r. So it rises. It has a cusp. Okay, it's cuspy towards the center. But in many galaxies that you observe, what you instead see is something like this, where the density profile flattens off, and what you have is that rho of r is basically a constant. So if you like, this is predicted, and this is observed in some galaxies. And if so the n-body simulations are not trivial. If you do pure n-body simulations, this is I think a very robust prediction. It has maybe slightly different slope than 1 over r at the very center, but very roughly it goes like this. But once you include baryons, which of course are part of the story, baryons will create supernova explosions. They'll drive out material from the central region that can drag dark matter with it, that could lower the density of the dark matter in the middle. Once you do that, things might work out fine, but it's not clear, I think, as of yet, how much supernova feedback you should put in, how much effect baryons have. So it's still sort of a little bit of an open problem. But that's one of the issues that people sometimes mention, the core cusp problem, that you predict often a cusp, what you observe in some galaxies is a core. Another problem which has, in principle, a simple solution is sometimes called the missing satellites problem. So I mentioned to you yesterday that in our Milky Way halo, we have a lot of smaller halos, dwarf galaxies. So it turns out that n-body simulations actually predict many, many, many small halos. And we only see a few of them. And that's been named the missing satellites problem. And that's also true for other galaxies. But so one possible resolution of this is that not all small dwarf galaxies will have enough gas in them to form stars so that we can actually see them. So it might just be that the small satellite galaxies are there, just we can't see them because they don't have any stars in them. So again, this depends on the baryons. When do you have enough gas in a halo to form stars that you can actually see them? Again, so baryons may again have a possible resolution to this. So another problem is called the too big to fail problem. So I just mentioned to you small halos that don't have any stars in them. Small halos that are not observed and that are predicted by n-body simulations. It turns out that even reasonably massive halos, still satellites, but still pretty massive satellites, also seem to be missing in the data. And that's harder to resolve with the reason I just gave here from baryons, because these are pretty big halos and they should not fail to have star formation. They're too big to fail to have star formation. So you can figure out just from the name of when this problem was invented. So in the US, there was a financial crisis around 2007. The banks were too big to fail, so you had to save them. But this is around the same time that also, this problem was sort of discovered, and some of these satellites are just too big to fail to have star formation. We should have seen them. Okay. And then finally, there is a diversity of rotation curves. So that's sort of an interesting problem. So if you look at galaxies, and you measure the stars in the galaxies, and you measure the stars, the velocity of the stars as a function of the radius from the inner part to the outer part. What you predict in lambda CDM is something like this. Okay, so first of all, the rotation curves, right, are evidence for dark matter. The reason this rotation curve doesn't go down to 0 at large radii is because dark matter exists and more dark matter comes in, which means the velocity of the stars at large radii are larger than they would be if they were just baryons, if there were just stars there. Okay, so you expect them to go down if there were no dark matter, but the presence of dark matter makes them flat. Okay, but basically, given some size of galaxy, so given some a large radius, some particular velocity, you can pretty much predict what it should look like as you go in. Instead, you can look at many different galaxies, and what you see is, you see sometimes this, but you also see this, you see this, you see a huge diversity in what the rotation curves look like. And it's not clear whether n-body simulations with baryons can actually reproduce this. So all these problems are sort of happening on small scales, okay, where structure formation will be affected by baryons. Including baryons in your n-body simulation is very difficult, but that may ultimately be just the resolution. But it might also point to interesting dark matter dynamics. In particular, the thing that particle physicists often talk about is the idea that dark matter has self-interactions. That dark matter can actually scatter with itself and transfer heat with itself. So that not that it's collisionless, but can actually interact with itself. In that case, that allows you to distribute heat from the outer part to the inner part of the halo, etc., which can actually flatten rotation curves. It could potentially explain this diversity in rotation curves here as well, and explain some of the other issues as well. And there's a very nice review by Sean Tulin and Haibo Yu on self-interacting dark matter. And if you're interested in these kind of topics, I suggest that you read this review, which I think is very nice. And it sort of lays out the different issues and how self-interacting dark matter in particular could potentially explain some of these things. So, self-interacting dark matter. And I think, so this is not yet clear if these are really problems. Okay, so particle physicists maybe, I think they're very interesting issues that need to be resolved. They might have a resolution with just baryonic feedback and baryons, including baryons in the simulations, which is very challenging. And there's many people working on that. Okay, so the standard n-body simulations, basically they include baryons. People are including baryons. So there's many different groups working on this. But from a particle physicist's point of view, it's interesting because it might point to dark matter having self-interactions. And the point for us is that dark matter with self-interactions, how can you get this? Well, you can get this if dark matter is part of a dark sector that has its own mediators. So if dark matter is able to interact with new mediators that can mediate self-interactions, you can actually get the right cross-section that you need to potentially explain some of these issues. Okay.
Are these two different measurements, the rotation curves and the density?
Yes.
Because how do you measure the density of? I thought you would measure the rotation curves and then.
Oh, so you need to measure. Yeah, you need to measure something about the baryons to infer the density profile. But so they're not necessarily. What I'm trying to say is that these are often different galaxies. Okay. But in many of these galaxies, you'll also have a core. Okay, so if you look at the density profile of these things, they'll have a core as well. Okay, of different degrees. Yeah.
So there should be a slight diversity in the core.
There'll also be, yeah. So there'll be different things here as well. Okay. So if you're interested in this, I think the paper on this, so this will have a review on it, but there was a paper by, I think, Oman, maybe 2015. So I'm not an expert on this stuff, but I refer you to that. Michael, you had a question?
Actually, I wanted to make a comment.
Yeah.
The only one of these problems that doesn't depend crucially on the simulation of baryon physics in the interior of the galaxy is the missing satellites problem. And the missing satellites problem seems to be getting solved. DES has found lots more Milky Way satellites. They tend to be dark and stripped of normal matter, presumably by tidal effects. So they're hard to find, but now they're being found. So maybe that should be crossed up for
So many of them are being found. I still think not enough, but I agree that this is probably the weakest of them all, just because it's easy to have, it's not surprising if very small halos just don't have enough gas in them to form stars. So I agree that this is probably the weakest of them. But I do want to mention it because it often still gets mentioned, but yeah, it's a good point, yeah.
And the too big to fail problem, did you mean too big sub-halos? Like
Too big, yeah, satellites that are...
Is DES finding those guys, the big ones?
No, not as far as I know, yeah. What they're finding is smaller things, yeah. Okay. So this is an interesting topic, and if you get particle physicists in the room together with n-body simulations, that's usually the topic that gets talked about. It's a lot of fun. And then everyone gets very confused. Yeah, but then they're just talking. They don't really know what they're talking about. So it's more fun if you do it with some experts. Yeah. Okay, but the point for us is again that if self-interactions are something that you want, you can't consider WIMPs because those self-interactions are tiny. They're of order picobarnish, right? And the self-interactions that you actually need for a GeV particle are of order QCD scales. So you need very large self-interactions actually to get the right relic to explain some of these issues. Okay, and you can do that with light mediators. So if you have light mediators or some non-abelian dark sector where the dark matter interacts strongly with itself, you can get these large cross sections. Okay, so for the rest of the lecture, what I want to do is I want to focus on this mass range really below a GeV, roughly here. So that's the remaining focus. And again, there's many things we could talk about along this mass range. We talked about axions and all that. That's super important. But I have to do something. I have to focus something. So that's what I'll do. Questions? Okay. Yeah.
So we just talked about the constraints for the case that the mediator is heavier than the dark matter itself. For the case where it's just the other way around, then it would hold the unitarity bond which we talked about yesterday. Is that correct?
Yeah, but it's still easy to evade that. So it's true that you can't make the dark matter too much heavier than the mediator. Otherwise, you get that issue again, potentially. Yeah.
Okay.
Mm-hmm. Well, sorry. So the unitarity bound, right, that just depended on the dark matter mass. Right?
Unitarity bound is
Yeah.
independent, yes.
And it's assuming thermal equilibrium, and so that's very high. So actually, no, so it's the unitarity bound is not important. But you're right that if the dark matter mass is heavier than the mediator, the cross-section dependence will change a little bit. So in particular, the cross-section will not go as m chi squared over mz squared, z prime to the fourth, but you can also get a dependence that's just this. Okay, but that's fine. Okay, so this is for light mediators, where basically the mass scale on the problem is going to be the mass of the dark matter. And again, this could happen for the same diagram that I drew. Where if you make this light, then the propagator basically consists of the energy flowing through this, and the energy flowing through this is given by the dark matter mass for non-relativistic particles. So everything will just depend on m chi, basically. So then the cross section goes 1 of m chi squared. Okay. So in the problem that I wrote down, I still made this a bit heavier. So that's why I still had this dependence like that. Okay, so let's now talk about dark sectors. And so I defined them already. So it's a collection of particles that's neutral under standard model forces, but interacting with some new force or several new forces. And the mass can be much less than the weak scale just because they're gauge singlets. So they're not charged under any of the standard model forces directly. So what we basically have is a sector which is the standard model sector with all the forces and particles in that. And then we've got some dark sector with its own forces and own particles. And the thing that makes it interesting is there's certain interactions between these two sectors. And these interactions we often call portals. And right, so the idea is, so dark matter could be part of the sector, and good. So now you can ask the question, which portals are important? Which interactions are important? And in principle, you have a very large number of them. Okay. But what you can ask is you can ask which are the most important. Okay. So not just some arbitrary thing, but which are the most important ones. And there's actually just a few of them. And they're basically dictated by the standard model symmetries. They're dictated by what the fields are in the standard model and what the symmetries are of the standard model. And in particular, so focus on most important. This is dictated by the standard model symmetries. And basically, if you tell me the particle, the spin properties of the particle in the dark sector, then we can write down the most important portal to that. So let's do that. Let me go here. So I'm going to erase this now. So if we have a scalar particle, some phi, then we can write down the following terms in the Lagrangian. Oops. Okay. So this for a scalar is often referred to as the Higgs portal. So what we have is we can write down h dagger h, which has dimension 2. That's just the Higgs field in the standard model. And this is gauge invariant by itself. And then we can attach a dark sector particle, a scalar in this case, phi, and we can attach it in two possible ways. We can write down lambda phi squared, h dagger h, or mu phi. And this is actually super renormalizable, mass dimension 3. So mu has dimensions of mass. Lambda here is dimensionless, and phi is mass dimension. So phi squared is mass dimension 2. So these are renormalizable. This is a renormalizable operator. And things that are renormalizable are important. Things that are non-renormalizable, sorry, let me be careful how I say this. So things that are renormalizable may have the largest interaction with us, okay? Because the interaction is not going to be suppressed by any mass or so, okay? So this interaction could potentially be large. So that's an important possible portal to a dark sector. So as for a scalar, we can write down a fermion. So fermion n, like a right-handed neutrino, which would be a standard model singlet. And in that case, we can write down a term that looks like this. And again, this has mass dimension 4. And this is called the neutrino portal. And again, what we have is we've got LH, which is gauge invariant. So L is the SU2, the lepton doublet, containing the neutrino and the electron, or the mu or the tau. And this is with the Higgs boson again. This is gauge invariant by itself. I attach a fermion, that's a standard model singlet, and I can write down this term. The mass dimension of this is again 4. Okay, so 3/2 plus 3/2 plus 1. And y would be a dimensionless constant. For a vector, which I'm going to call A prime, for reasons of normalization, I'm going to write it like this. But there's some epsilon over 2 cosine theta w. Theta w is the Weinberg mixing angle, or the weak mixing angle. And this is a Fy mu nu times F prime mu nu. So what we have here is a hidden U1, so a abelian gauge group in the hidden sector that's mediated, whose mediator is this A prime here, the vector boson. And the interaction is this interaction here, which is called kinetic mixing, and this is called the vector portal. And that's the one we'll focus on most in these remaining lectures, in the remaining time of the lectures. And so I'll explain that in a minute a bit more. But notice that this one here, so this is gauge invariant, this is a hypercharge, okay, hypercharge of the standard model. The hypercharge in the standard model is a U1 abelian gauge group. This is gauge invariant by itself. I can attach the F prime mu nu, and I can put these together. This is dimension 4 again, and then there's some constant in front, epsilon, and I've normalized in some way for technical reasons, which right now are not important. But basically, we've got, again, this constant that's dimensionless times the dimension 4 operator. Okay. You can't do that with other abelian gauge groups, by the way. You can't take the SU2 fields and attach another dark SU2, just because that would not be gauge invariant. But the thing that is gauge invariant is the U1. Okay, so I can write this down. And that's called the vector portal, or sometimes also called the kinetic mixing. Kinetic mixing because the field strengths in here, right, F mu nu, generically for some gauge field A, F mu nu will look like this, and that contains the kinetic energy terms. So often this is called kinetic mixing. So you're mixing the kinetic energy terms of the two U1 fields, some dark U1, which is in some hidden sector, and the hypercharge. And then finally, pseudoscalar. So instead of having a scalar, I can have a pseudoscalar, which is parity odd. And in that case, I can write down a coupling that looks like this. Where F mu nu tilde are standard model fields. So those could be the U1, the SU2 or SU3 fields, QCD. And that's basically what Nathaniel wrote down yesterday. So I'll let him explain a bit more tomorrow when he continues about this term. We're not going to talk much about it. But that's basically how an axion or an axion-like particle would couple. And the difference here between the other portals and this one is that this is dimension 5. Okay, so this is suppressed by some high mass scale F. F is A is the axion field, right? That's the new field. That's the pseudoscalar, and F is some constant mass dimension, massive dimension 1 constant, and it's dimension 5. But often this is very difficult to probe. Well, it is very difficult to probe if I make F very large. If I make FA very large, in that case, I can suppress the interaction of the A with these gauge fields. Okay, by making FA large. Okay, so those are sort of the most important portals. Yeah.
But axion degree constant is pretty well constant, right? Like you cannot make it very large. It's like it has to be around 10 per 10 or like 10 per 16 GB or something, not more than that.
No, you can make it larger. For the QCD axion, or for generic axions, you can make it larger. Why not? Or what bound are you worried about?
Don't you have any like landscape problem or something related to it?
Well, so there's discussions about this. So things might become fine-tuned, and then also there's a paper recently by Peter Graham, and I apologize, forget the collaborator, which was a few months ago, which talked about ways to get a very large FAs. Okay, so you can look at that. But yeah. Mm-hmm.
So we use the vector A prime. Does it have a mass? Is massless? And if it has a
So,
mass, how does it
yeah.
get it?
So I'm imagining a massive thing, and I can get it from different ways. So one thing is just the Higgs mechanism. So you can imagine some dark Higgs, which just like our standard model Higgs gives mass to the W and Z bosons. We can imagine a dark Higgs giving a dark Higgs mechanism, giving some vacuum expectation value, which gives mass to the dark vector. Okay, so I'll go into that in more detail in a few minutes. Not the mass generation, which is why I'm mentioning it now, but I'll go into more detail of kinetic mixing in a minute. Okay.
Did you say that it could be massive or massless?
It could be massive or massless. So I'll focus on the massive case. This could be massless, in which case, if there's any other dark sector particles, those will be milli-charged. They would have a small electric charge. Okay, I'll mention that when I get into more detail in a second. Okay, so those are the portals, and so it's not like anything goes, right? If you're asking what the most important ones are, these are good ones to study. The other thing we could do is we can couple to B minus L or B or L just in the standard model with some effort. We can do that as well. So we want to look at not just this particular portal where you're mixing with a hypercharge, but look at general sort of Z prime models where this A prime or Z prime, it has different names depending on who gives lectures, but those will couple to leptons predominantly, or to baryons, or to both. Okay. So the way I've written it down here, as you'll see, basically with the way this dark photon couples, this A prime, it's going to couple to electric charge. Okay. And I'll go into that in a second. Okay. So all these portals are interesting, and we'll focus on the vector. Okay, so let's get into some kinetic mixing basics, vector portal. Where's my little thing? And what I want to do is I want to focus on that portal, explain to you a little bit how the interactions work between the dark photon and the standard model particles, given this, and then talk about searches for this. And you'll see just this simple little thing, just the variety of knowledge you can get just from that, and how many different searches you can potentially do and would want to do. All right, so for more details, I think there's quite a few references now, but these are some that I know. Okay. So, right, so what we have is a dark sector with a hidden U1, so some abelian gauge group. I will imagine that it's broken. So just like SU2 cross U1 is broken in the standard model, SU2 cross U1 hypercharge is broken down to U1 electromagnetism, where we have three massive gauge bosons, the W plus, W minus, and Z. By breaking the gauge group, we have a massive mediator now. And again, how it's broken, you can imagine some dark Higgs mechanism, just for simplicity, although that's not the only option. So I'll denote the mediator as I did here by A prime. As I said, depending on who gives lectures, you'll either get a U or an A sub D or a V or Z prime. And we are interested basically at effects at low energies. By low energies, I mean well below the weak scale, so below the scale of electroweak breaking. And in that case, we don't talk about hypercharge anymore, but actually what happens is that the kinetic mixing is basically with the unbroken gauge group, which is electromagnetism. So the kinetic mixing is going to be between this hidden U1 and electromagnetism at low energies. And we can write down a Lagrangian, which will contain various terms. So here's the terms for U1 electromagnetism, the kinetic energy terms. Here are the terms for the dark U1. And then I've got this term here, the kinetic mixing term. And now because I'm writing it now not as with hypercharge, but with U1 electromagnetism, I'm going to remove the cosine theta w. So I'm not explaining this why, but basically this is what happens. That's why I had it here, just to be sort of consistent with what I mean with epsilon. So the epsilon here is the same as the epsilon there, but mixing is now with the standard model photon. Then I want a mass. So we have some massive gauge boson now. And I've got an interaction between the photon and the electromagnetic current, of course. Okay, that's just the electromagnetic current. So these are all the electrically charged fermions in the standard model. And I've got an interaction potentially of the dark photon with some dark current. Okay, so I can imagine the existence of additional dark fermions which are charged under the hidden U1, and that could be the dark matter, for example. Okay, so the dark matter could be part of this current here. And so let me just write down. Right, so U1, so J electromagnetism is just going to be the sum of all the fermions with the charge F bar gamma mu F, and J dark mu is going to be interaction of the dark photon. Well, it's going to contain some dark fermions, or scalars if you like. And here I wrote down a fermion, and this could be dark matter. So this is a very simple dark sector, and let's see what it does. So first of all, we want to simplify this interaction a little bit. So it's fine to work with the Lagrangian, but it's actually easier to simplify things a little bit. So first of all, this term means that things are not quite diagonalized. Okay, so we have this mixing term here between the dark U1 and the electromagnetism, and what we can do is we can redefine fields to remove this. And this is a useful exercise. So I'll tell you what you have to do to redefine the fields, but then it's actually good to just do it yourself. So that's an exercise. So we can redefine the fields. That doesn't change the physics, of course, but it simplifies how to look at it in some cases. So do field redefinition to remove kinetic mixing. And what we'll do is we'll take the A prime, we'll leave unchanged, but the electromagnetic field, so the F mu, that's the electromagnetic field, and just to make sure, so that doesn't have a prime, right? So F mu here is just this, and my A is the photon, and the A prime is the dark vector. So I'll redefine this. And of course, these have mu's on them. Okay. So I'm basically rotating my photon field a little bit. And then what you do is you just put those into the Lagrangian, and you do this complicated thing called algebra, and you see what happens. And then what you get at the end is the following. So we just care about a few things. So one thing that you see is if I look at this term here, A mu, J mu, this A mu is going to get transformed. And in particular, I'm going to get a term that's going to contain epsilon A prime times electromagnetic current. So this removes the field, the kinetic mixing. You can check that. So check that mixing term is removed. A leading order, at least, in epsilon. And the A prime, the E, A mu, J mu electromagnetism is going to now consist of two terms. One of them just the same as before with a photon, but now there's also an additional term, which is epsilon E, A prime mu, J E M mu. Okay. And what this means is that all standard model electrically charged particles, so everything in this electromagnetic current, all the quarks, all the charged leptons, will have now an interaction with this dark photon, this A prime, with an interaction strength that's given by epsilon E. So it's like a photon, except interaction strength that's suppressed by this epsilon, which at this stage is arbitrary. And this is why we call it a dark photon, or a heavy photon. Okay, so it's like a photon, except it has a mass, so it's heavy, and also its interaction is like that, a photon, except suppressed by some epsilon. Okay.
Is epsilon a small number? Epsilon has nothing to do with this epsilon, is that right?
This epsilon
Yes.
is the same as that epsilon.
The same.
Yeah. That's the same as this epsilon. So they're all the same epsilon. It's arbitrary at this stage, yeah. We haven't said yet anything about it. Okay. I'll make some comments about that in a minute. Okay, so all standard model electrically charged particles have a, if you like, you can say they have a dark Milli charge. Okay, they're charged a little bit under this dark U1. And diagrammatically, what we have is the following. So we've got some standard model charged particle. It interacts with the photon. Okay, so looking at it in this basis over there with the kinetic mixing, all standard model charged particles have an interaction with the photon. That's given by this. This vertex here is just E times the charge of the fermion that we're considering. But then there's this kinetic mixing with this dark photon, which I can draw like that. And this kinetic mixing is given by epsilon. And if I do this carefully with all the momentum dependence in the diagram, so notice that here I've got derivatives, so those will turn into momenta. So this is basically epsilon q squared, the photon propagator. So if I think of this as a Feynman diagram with the A prime attached to these fermions, in that basis on the right side with the kinetic mixing, the way it interacts is that there's this kinetic mixing, which is epsilon q squared. The q comes from the derivatives. And then the photon has a 1 over q squared here, couples to the standard model fermions with EQF. And you see that this is equivalent to the basis over there, which is after removing the kinetic mixing, where what I have is a dark photon with an interaction strength that's given by epsilon E QF. Okay. So epsilon q squared over 1 over q squared times E QF is just, you can just imagine this in this space on the left side from your point of view. Then you have this interaction strength. Okay, so it's like a photon except suppressed by epsilon, and the A prime has a mass. Questions?
Yeah, do we then say that every photon comes with a dark, together with a dark photon somehow?
So if I interpret your question, the answer is yes, if I interpret it in a certain way. So yes, so basically wherever you've got a photon, you can imagine that you can also have a dark photon. Okay. Okay. By the way, this means there's also, as an aside, the dark sector, the dark matter, and the chi's in the dark sector, they do not get a small electric charge. They're not milli-charged particles. They do not have an electric charge. Okay, and the reason is that we can turn this diagram, or reinterpret this diagram for the chi's. What you have for the chi's is this. So they couple to the dark photon. And if I imagine interacting this with the photon here, you might think that because these interact with the photon, they have a small electric charge. They do not, because an electric charge has to happen at zero momentum. So if I look at all these diagrams, if I do the same thing as I did up here with all the correct vertices, what I have is this, and this basically will scale as epsilon g dark q squared over q squared minus ma prime squared, and that goes to 0 for q goes to 0. So the chi's are not electrically charged. Okay, they can still interact with the photon through off-shell processes, but they don't actually have an electric charge. Okay.
And that's because it's massive.
That's because it's massive. So once you make it massless, then you have then you've got milli-charges. Okay. But yeah, basically, I mean, of course the massless case is interesting to consider, but we won't do that more. Okay, so now we have a very simple dark sector, which does an amazing amount of, gives amazing amounts of phenology. And to begin with, we're going to simplify things a little bit. We're going to consider that any dark sector fermions, like dark matter or so, is heavy. We don't care about it. Okay, we just make it heavy. We decouple it from the theory. We either don't make it present at all. We just remove them completely. But we don't care. We just make it heavy. Okay, we're going to look at that, and then in a while, for our next lecture, we'll bring the dark sectors back in, the dark matter back in, and see how the phenology is potentially changed. All right. And another important point is that you'll see this type of model, kinetic mixing, you'll see very often. So you'll see it as a basic building block for more complicated dark sectors. So you might consider a non-abelian dark sector, but the way you make it interact with the standard model is through kinetic mixing. So the dark sector might be complicated with lots of hidden sector gauge bosons, some non-abelian theory, but if you want to connect it, people often connect it with a kinetic by kinetic mixing with a dark U1. Okay, so it's good to know just the basic phenology of this. And then another thing is, because we have this, so this dark sector also has self-interactions among dark matter particles, if you like. So the chi's interact with the dark photons, of course. They're charged under them. You can write down diagrams where the chi interacts with itself. Okay, so let me just make this comment. So this simple dark sector is very rich and has a lot of homology. It's the basic building block for more complicated dark sectors. Let me just say often, of course, we talked about, we already mentioned other possible dark sectors, but this one is often a basic building block for more complicated dark sectors with non-abelian and just another comment, so chi can have self-interactions, which I said half an hour ago why that might be interesting for dark matter. So simply from this diagram here, the chi can scatter with itself. Okay, and if you make the A prime, the mass small enough, and you make the mass ratios correct, and you put the right coupling, you can easily get a QCD scale cross section if you want to, which is what you need again to explain some of these SIDMs, these self-interaction, these small scale anomalies. Okay, so for now, let's see what guards. Okay, good. So for now, let's focus on A prime alone, i.e. decouple or ignore the chi. Okay. And we'll see what we can do. Okay, so before I've discussed homology, well, okay, first of all, let me pause for a second and ask if there's any questions. Okay. Okay, and so before I actually talk about the homology, how to search for the dark photon, let me quickly make comments about the parameters in the model. So the important parameters in the model are very few. So there's epsilon, right? So epsilon is obviously an important parameter and tells you the strength of the interaction. The dark photon mass is the other one. And if we ignore dark matter, that's it. Okay, that's basically determines the whole homology. I'll just comment, I won't discuss in any detail. If someone asked the question earlier, how does this dark photon get its mass? And I said one possibility is through the dark Higgs mechanism. In that case, there would be a dark Higgs, right? That would be part of the story. And then that can actually change the homology. But you can consider a case where the dark Higgs is a bit heavier than the dark photon, and then again, you can sort of go into a limit where the dark Higgs doesn't matter. Okay, so we'll take that just to simplify things. But in principle, there's a dark Higgs hanging around as well. But those are the important parameters, and if we include dark matter, then the dark matter mass and this thing I call the G dark. Yeah, okay. So, so the gauge coupling of the dark matter to the dark photon, those are also important.
So you have a dark depth, a dark spectrum, and completely independent from the non-dark one? I mean,
Say again?
The dark Higgs mechanism, you would have, from the end of the day, a dark vacuum sufficient value, completely independent from the non-dark one?
Yeah, yeah, you can imagine that. Yeah. Okay. Right, so the way I would do that is just write down a dark Higgs that is charged under the hidden U1, and then just like the way we do in the standard model, you can write down the same type of interactions. And it's easier because it's just abelian. Right. Okay, so what are the values? So the basic answer is that epsilon and MA prime are arbitrary. Okay, so they're completely arbitrary, and we in principle want to look for a wide variety of masses and couplings. But in certain scenarios, you can predict them, which means that by additional model assumptions, you can say what the mass range should be. So also, depending on what you're trying to do with this dark sector, there are, if you're interested in explaining certain anomalies, that also will fix or say what the values should be. So I'll mention anomaly probably next lecture. Maybe I'll get to this lecture. But where you can use the dark photon to explain the discrepancy between the calculated value and the measured value of the anomalous magnetic moment of the muon. And in that case, you actually have a very sharp prediction of what epsilon and MA prime should be. Okay, and or if you want to explain the self-interactions among dark matter, then that requires if you have some dark matter mass and some, basically you can try to find parameter regions of G dark and M chi and what the MA prime needs to be in order to explain the right self-interaction strength. So in certain scenarios, you have sort of phonology that tells you what it should be. Okay, but from a theoretical point of view, they're really arbitrary. And so epsilon in particular, it's a marginal parameter, right? It's you just have some dimension 4 coupling. It's basically a UV boundary condition. It's set by some whatever happens at the high scale. What you can do is you can say, well, let's imagine that the standard model gauge groups unify in some grand unified theory. So above the grand unified theory scale, above the gut scale, there wouldn't be any kinetic mixing because there's no free U1 hypercharge. So it would be 0 at the gut scale. And then below the gut scale, you can try and generate the kinetic mixing. And in that case, you can make sort of guesstimates for what the range should be. So let me write that down. So epsilon is marginal. And it's basically a UV boundary condition. But if epsilon is 0 at some high scale, for example, if you have a grand unified theory, so then there's no U1 hypercharge at above the gut scale, in which case you don't have any kinetic mixing, but it gets generated below that, and then you can generate epsilon by fields that are charged under the dark U1 and the U1 hypercharge. And diagrammatically, the way this looks is as follows. So very simple. You have the dark U1, and you've got the hypercharge field, which I'm denoting by B here. And there's some loop of particles which are charged under, so I'm denoting these by X, fields charged under both U1 prime and U1y. Then you can get a diagram like this. And let's say these are very heavy, just below the gut scale, for example. And then you can calculate what epsilon should be. And what you find is that epsilon is going to scale as the couplings here and here. So there's some G dark coupling there. There's some G, let's call it G1 coupling there. So G dark, G1. There's a loop here, so there's a 16 pi squared. And then there's a log, which you get, which basically depends on lambda and the mass the x's. And depending on what parameters you choose, you can of course get anything. You can make these couplings arbitrarily small or so, but if you choose sort of reasonable numbers, 0.1-ish, 0.01 or something like that, and you choose reasonable numbers for, like choose lambda to be the gut scale and mx to be some lower scale, very roughly the log will basically make any large hierarchies here, the log will always make it a smallish number. So roughly what you can get is 10 to the minus 3. But there's of course a large range, so this really depends on GDoc and the properties of these X particles. Exactly how they interact and what the charges are. But again, so I'm not going to spend more time on this. Basically, in certain scenarios you can you can get predictions for this. You can also imagine scenarios where the kinetic mixing is generated by 2 loops. Then you've got 2 factors of 1 over 16 pi squared. So then you would get 10 to the minus 5 or so. But in principle, it's an arbitrary thing. So you want to explore as much as you can. Okay. And same with the dark photon mass. It's basically set. It's not set by anything. It just really depends on, in certain regions, parameter space, there's very strong constraints on the mass, as we'll see, and other regions it's much less constrained. And as I said, there's certain regions that are motivated by phenomenology from the anomalous magnetic moment of the muon, for example, that anomaly, and I'll mention that in a bit. Okay. I mean, back in 2008, 2009, when I was mentioning yesterday, all these anomalies were from dark matter were about, and all these anomalies were around. Then people started using these dark sectors to explain some of these anomalies, and in that case, people tried to embed this in supersymmetry and explain where the dark photon, where dark photon masses can come from, and they were very interested in the sub-GeV scale. And they embedded this in supersymmetry and try to make models where you can actually get the GeV scale out. So that's possible. And I'll just give you some reference if you're interested. Let me write this here. So for MA prime, there's references which 0904.2567 and 0902.3246. Okay. All right. Good. Questions on this? You mean if you, right, not the kinetic mixing, but just the final Lagrangian?
You mentioned you can remove the kinetic mixing by using up front the interactions that are removed there.
Yeah, well, that's just a field definition. It's the same Lagrangian. So I can rotate one to the other. It's just a change of basis.
Correct, yeah.
Yeah.
Is there a problem with the word identities having generated an epsilon back into
No, I mean this is a broken gauge group, like the U1 prime, right? I don't see any problems. We can talk afterwards about what you're worried about, maybe, but yeah. Okay, yeah.
You presented this to us because it's particularly simple, right? Actually, you could also take another gauge group, and this would be like the same story.
Another hidden gauge group, or what do you mean?
No, I mean, like you had this U1 prime, but you could like extend by a dark W also.
Ah, so no, though. So that's not as simple, right? So the kinetic mixing is this with hypercharge or with a photon, the way I presented it in detail. If you make this something else, like SU2, then there's another gauge group index here, and this is not gauge invariant by itself, right? In that case, you have to somehow make it gauge invariant, and you cannot. So you can only do that if you have some more complicated setup then, but that's not going to be a dimension 4 operator.
Nobody does things like that.
So people have considered that. I just don't have a good reference for that, but that's not usually done because it's okay thing to do, but it's more complicated and it's going to be a higher dimension operator because that's not gauge invariant by itself, right? Whereas this is with just an abelian gauge group. Okay.
When you did for the Y for the hypercharge, there is also kinetic mixing between that guy and the Z also, not only the photon.
That's right. So if you're super careful about it, if you make this really hypercharge and you rotate all the fields correctly, there's also going to be a mixing with the Z. But at low masses, which is what the assumption was, that's suppressed. Okay. So basically what happens then at low masses is that for the low dark photon masses is that the dark photon really acts just like couples to electric charge, almost exactly. Okay. So if you're interested in the more details, the reference that I gave at the beginning, those actually discuss the more general case. Okay. Other questions? Okay. Let's see. So I have 5 minutes. 5 minutes are important. Let me start, and then I'll start again this afternoon. Yeah, you've got 2 lectures today from me, sorry. I'll start now, and then I'll just start again in the same place later today, but I can go a bit quicker this afternoon. What I want to do, I want to get rid of this here. All right, so what we'll do now is we'll look at the dark photon by itself, and look at its interaction, look how it can be produced and what it does. Just pure dark photon. Okay, simplest thing. So, no chi, no dark Higgs, etc. So the first thing to understand the phenology of the dark photon is, one of the first things you can do is you can ask, how does it decay? So if you were to produce it, how does it decay? And there's 2 very different mass ranges. The mass range either above twice the electron mass or below, and the phenology is very different. Okay. Above twice the electron mass, it can decay at least 2 electrons. Okay. So we at least have this. And this again is going to be epsilon times E, this interaction here, or epsilon times QF more generally. And below twice the electron mass, it doesn't interact with any charge. There's no charged fermions lighter than the electron. In which case, the only way that the dark photon can decay is through 3 photons. There's also neutrino decay, but it's super slow. It's much slower. But what it can do is it can go through a loop to 3 photons. And this is super, super slow, and this can be very fast, okay, depending on epsilon. So I keep writing 1 and 2. I'll keep doing that. So let's go back to 1 and look at that in a bit more detail. So if we just take the simplest example, E plus E minus, the decay rate of the A prime to E plus E minus is going to be given by what? What is that equal to? So you're not going to, if you haven't done this before, you're not going to get the exact numerical factors correct, but dimensional analysis is very powerful, and you should be able to figure out just what the decay rate will depend on. So who wants to guess? 1/2 times the mass. 1/2 means a half. That's what you mean? Yeah. Sorry, no, I just want to make sure I understood. Times this?
Mass of the electron in
Like this?
No, that only in a then
That's it?
yeah, there should be something. I don't know. Well, I think you could put the mass of the M prime in the denominator because it's already there from the flux factor.
So we have two suggestions, this or this. What's the mass dimension of gamma? So you all think 1/m? No, bad.
The accessible phase space needs to be important, so you need a mass of VA minus 2.
There's phase space, yeah. Make it heavy. You're right, but make it much heavier than the electron, yeah. So what's the mass dimension of gamma?
1/time, which is energy.
1/time, which is energy, which is mass. So there has to be a numerator, okay? So, and if I make it much heavier than this, the only thing of relevance is this, okay? So it has to be that. And if I look at the couplings, so this is going to be epsilon times the electric charge. So I'm going to have here an epsilon squared, right? Amplitude is epsilon squared to get the decay rate. And there's going to be E squared, which is basically an alpha with the probative factors of 4 pi. Okay, so this has to be the rough scaling. And now if you want to get everything correct, turns out there's a factor of 1/3 here. And then, as you were saying in the back, there's the phase space. So that's going to be there. Times by 1 plus 2 ma prime squared over, me squared over ma prime squared. Okay, so those factors are from phase space. They're not important if ma prime is very heavy, but here they are, if you want to include that. And yeah, that's what you have. Okay. As a general comment, so this dimensional analysis is, of course, in some ways it's trivial, but it's super powerful in many cases. And you can just often guess cross sections and decay rates and so on. And just to get intuition from things, it's often useful just to do that exercise. And I remember when I was in undergrad, I would do this summer project with my advisor, and he would give me some calculation to do. I would work 5 hours and come back, and he looks at it for 2 seconds and says, "This is wrong." I'm like, "Why? How do you know this?" It's dimensional analysis, okay? So that was a big insight for me, that just using dimensional analysis, you can actually check things a lot. So anyway, this is useful. But this is the exact answer, and I'll stop here. I better stop here, otherwise I'm going to get in trouble. And we'll continue from this. So we'll look at the decays, then we'll talk about the production of the pure dark photon case. I'll mention a whole bunch of different ways to look for it, and then we'll take the dark matter, we bring it down again in mass, and we have the dark photon not decay to standard model particles, but actually decay to dark matter, and see how that changes such as a collides. And then the final lecture, we'll look at direct detection. So we'll turn the diagram around, and we'll look at scattering that could be mediated by a dark photon as well, but we'll make it more general. But we'll have scattering of standard model particles through, for example, dark photon, where the mass of this is very light. Okay, that'll be the final lecture then. Okay, that's all. Thanks.